Welcome back to High Tech Heroes. Our guest this week is Howard Knoebel, and he's here to show us his latest project, which is a sawmill that you built, right? So what did you build the sawmill out of?
Well, I retired from the university, over 10 years ago, and moved to the place in the country which has about 140 acres of woods. And as part of that, I built the sawmill. I also have a wood shop and a machine shop there.
You build the buildings to house all of those?
Yes, the sawmill sawed the wood for its own building.
Oh, I see. Well, that's interesting. I guess
so
we
I
have
had to work
compilers that compile themselves, and
right.
sawmills that house themselves.
That's correct.
Well, I think we have some tape of that we could see if David Fry, our director here, can roll the tape. But this tape, I guess, yeah, here we go. There you are, Howard.
Yeah, that's me at the operating position, moving the log out a little bit closer to the blade. And then I guess we just finished a cut. There was some
that looks dangerous to me, reaching up close to that blade. But I guess
the engine is just idling right now. It's driven by an automobile engine.
Now you can see the automobile engine sort of back behind you there.
Now that's opening the throttle to the governed speed. And the different lever causes the carriage to carry the log into the saw blade.
Wow.
And there you can see how it cuts off the first slice.
Now the speed to the blade doesn't seem to change even in the log.
No, there's a governor added to the engine, a flyball governor. It took me about 2 weeks of mathematics to figure out the parameters for that. With electronic systems, you can have gain controls and various adjustments to get a stable system. But for the mechanical ones, it isn't easy to make changes, so you have to get everything right first time.
Now this is the bed, I guess, that we're seeing where you have some cables.
Now the carriage is going through again, sawing another slice off the log. It's pulled by steel cables that wrap around the drum. And the drum can be turned in either direction by belt and gear drive. The slipping belt track is the clutch. That's the tractor that's used for lifting the logs on. And in the background is a building which contains a dryer for kiln drying the hardwood lumber.
Right. So you dry the lumber there.
And I use that lumber for making furniture, trimming the house, and things like that. This round building, my wife and I built by ourselves without any outside help. That contains the machine shop and the wood shop.
I notice it has a 7-pointed star there on the door. Does that have any significance?
The 7 points refers to the symmetry of the building. The roof is made from plywood cut in such a way that there is no waste. And to get a nicely proportioned roof, it took 7 of these big triangles.
Now that means no waste from 4 by 8 sheets of plywood?
That's right. It's cut on the diagonal, and all of the triangular pieces were used.
And all the angles worked out? I guess you set the slope of the roof so that...
No, you let the plywood determine the slope, and you have a choice of several, and you choose the one that's architecturally the best.
Well, that's an interesting way to design, but 7-sided is pretty unusual, I think.
Well, that's just because that gave a more reasonable slope. As I recollect, 6-sided didn't have any good options from the 4 by 8 sheet.
Right.
Others that work out nicely are 12-sides, though.
What about the sawmill? Now, that was built all from scratch? You have...
Mostly. Some of the things are purchased, the mandrel and a few things like that.
Well, you didn't build the engine.
At that time, no, it's an automobile engine, and the differential are all there. Automobiles have a good profile for a sawmill. At the university, we did some railroad wheel testing using a Cadillac engine, but the engine would only last a very short time, a couple of months, because we would run it at 100 horsepower for 5 minutes. The car engine isn't designed to run at that high level for so long.
Right.
The manifolds would get red hot and everything, but the sawmill fits the profile of the car engine in that the log is sawed in about 10 or 20 seconds, and then it cools off while you bring the log back. So you can run your engine at several hundred horsepower for a little while.
Yeah, but low duty cycle. And so you bought that engine new? You buy that from J.C.
No,
Whitney?
I bought a used car. The university bought last year Cadillacs for $300. And I inquired how you go about doing that. So you have to kind of follow the insurance adjuster and make a deal with him before it gets any further. Because once a damaged car in an accident gets in the hands of a salvager, then the price goes way up.
I see, because they know what it's worth, apparently.
Yes, and they're not taking any risk anymore. When they know they have a good engine, then it'll be $1,500.
Right, right. Now, you say you designed this governor. I could see it in the background a little bit in the video. It has, you say it's a flying ball?
It has two flyweights supported on cantilever springs, so and as the weights move out,
they move out. Okay.
They move out, you know, to a certain constant position, and from there on, it causes the throttle to close as they move out further.
And then you change that that goal state with your lever.
There's an additional coil spring which aids these cantilever springs, which are rotating, and by stretching that coil spring can make small adjustments in the operating speed.
Right, right. Now, the cable bed is just what? It's just pulleys and...
It runs back and forth on wheels which ride on angle irons. And those angle irons are supported on wood timbers.
And you bolted all that together, or welded all that together?
Yes, and the wood timbers are supported on concrete piers that were poured, you know, into the ground.
Now, what does it take to make a wood dryer, or this wood kiln?
Well, I made use of a 15,000-gallon oil tank. It takes a relatively impermeable structure. If it's going to be a building, it has to be more moisture tight than customary, because the big problem in drying hardwood is to keep it from drying too fast and causing cracks.
I see.
The high temperature allows the moisture from the interior to diffuse to the exterior. Okay. And you don't want to let the exterior dry too fast, so you keep the humidity in.
But it has to be a humidity and temperature controlled environment then.
Oh, yes.
And so you sealed the whole thing by building it inside this, was it really an underground tank for a filling station?
At one time, yes.
And they dug that up. I guess it leaked a little bit too much for their purposes, or?
No, it's just the EPA is causing them to get rid of metal tanks.
Oh.
Because of the potential for leaking.
Oh, I understand. Well, that's interesting. So it's a perfectly good tank.
Yes. Oh, it had a few dents in it because the bulldozer that removed it dented it, and I had to remove the dents.
And you have a complete machine shop there, too, I guess.
Yes. I even had some of the machinery when I worked at the university because they had discontinued the student shop, and I thought that some of these facilities were essential. So I, at that time, bought a lathe and had it in my office. But since I've gone to the country, I have bought other machinery so I can do almost anything that's needed now.
So you have what? You have a lathe?
I have two lathes there, and I have a milling machine and several drill presses, grinder, and things like that.
But you don't have just rough-hewn lumber. You can then you can finish the lumber.
Oh, I have in the woodworking machinery. I have two planers, which you know, smooth the surface and make it of uniform thickness.
Right.
And then I have all the other conventional woodworking tools, such as you know, the table saw, band saw.
So you can make furniture, or make.
Yes.
No, that's
I learned furniture making when I was in high school.
Oh, I see. Furniture making and cabinet making.
Yes.
So now, when you were at CSL, I think you had one of the first computers I ever saw, but it was an analog computer, I think.
Yes, we had a Beckman analog computer.
And this is the Beckman from Beckman Instruments?
The Beckman who founded Beckman Instruments, yes.
Now that's close to where I live now.
Right.
But, I guess he has a building here on campus now as well.
Well, he donated about $10 million toward the construction of the Beckman Center.
And what exactly was that? I mean, that was used simulation of analog techniques to simulate different...
Well, the digital computers were in their infancy at that time. And analog computers were used to a great extent, primarily for dealing with differential equations. You have integrators in the analog computer, and
that's easy for an analog computer. It's it takes a lot of iterations for a digital computer to to integrate usually.
See, the analog computer is highly parallel. You have a separate electronic box for each integration that's going on.
Yes. Well, we're starting to see some of that with digital things, with neural nets. But now, also, I guess you mentioned something about an optical gyroscope. What is an optical gyroscope?
Well, that's was proposed some 30 years ago also. I didn't work on that, but other people have,
Right,
and I understand recently that they have been in practical use. It consists of a set of prisms or mirrors so that a light beam is traversing a circle clockwise, and another light beam from the same source traversing the same circle counterclockwise.
Now, this is bouncing off of mirrors, or?
Yes.
Okay.
It could be 4 mirrors to form a square, whatever you want. And then the 2 beams interfere at a certain point.
So sort of like a Michelson-Morley experiment. So you have an
you
interferometer
get
anyway.
the refraction pattern. And now, if the whole apparatus is rotated in inertial space, by rotating, say the clockwise beam is going upstream and the counterclockwise beam is going downstream, the diffraction pattern moves over.
So it changes a little bit, and you can tell, well, you can tell you rotated.
You can tell the rate of rotation. And many gyroscopes are what they call rate gyros. The one we described today is a direction gyro.
Right.
But for
So
most,
it really uses the axis direction, but then...
see, the rate gyro is good for guiding missiles and things like that, to keep it stabilized in the direction that it's going.
Well, that's, now a rate gyro, you say, that has to do with the rate of
It just gives
rotation
you
instead of
the rate of
direction
rotation of its housing.
I see.
Just the derivative of the direction.
And you can tell enough then from the Doppler shift from the, I guess, from the light beams is what you're really seeing.
That's what causes the diffraction pattern to move when the apparatus is being rotated.
So this isn't really the momentum of the photons then?
I think it's...
You think it really is?
It's
in the final
related to
analysis,
that.
huh? Okay. And with the sounding rockets, you measured the rotation of the Faraday rotation.
Faraday
of the
rotation
ionosphere,
due
right?
to the ionization in the upper atmosphere.
And what does that have a direct effect on anything, or is that the same thing they measure?
Well, it's say related to the to radio propagation, the E layer and things like that, and the measurement would measure what the electron density was as a function of the various heights.
Right.
We would measure up to about 100 kilometers.
I see. But mostly that, now I know they measure in chemistry, you measure often the angle of polarization or change of angle of polarization for different solutions, and you can identify things. The same kind of...
Same kind of thing. The presence of the electrons and the Earth's magnetic field causes the polarization of the radio waves to be rotated.
Right, great. Well, we have to take off now, but thank you very much for
I certainly
coming by.
enjoyed talking with you, Sherwin.
It's great to see you, and we'll have to see some more of your toys next time. And
Okay.
be sure to tune in to High Tech Heroes again next week. Au revoir.
Thank you for joining us this week for High Tech Heroes. Be sure to watch High Tech Heroes again next week, when we will bring you more entertaining information about the people and ideas behind the scenes in high-tech industry. And now, this is your announcer, Margie Foote, wishing you the best of luck and a pleasant week. Au revoir. This episode of High Tech Heroes has been made possible in part by grants from Linksys Incorporated of Lafayette, Indiana, and Cybernetic Arts of Sunnyvale, California.